Camera died, so I'm going to pick up where it cut off. Oops, wrong one. So we got that our radius was 18 with a bunch of zeros. Because we added them together, we were going to use velocity as square root of gm over r. We have our radius, we know g. Now we just need to be careful with which mass we use. We're not using the mass of the satellite, we're using the mass of the center object, which in this case is the moon. And the mass of the moon is given up here, 7.35 e22. Plug into your calculator, you get that the velocity is 1654. And then now we're looking for our period. Period is 2 pi r over v. 2 pi radius we just found is the 18, a lot of zeros, over our velocity. So then into your calculator, I got that my period was 68.37 seconds. 28, one of the Saturn's moons is named Mimas, the orbital radius. So here I don't need to add, I was given the radius. The orbital periods, this is the capital T. I'm going to find the mass. So I first am going to use my 2 pi r over v equation to get the velocity. So 82,800 equals 2 pi radius over v. If your unknown's on the bottom, the first thing we should do is multiply this up. Now I have v times 82,800. I'm trying to get v by itself, so I need to get rid of the 82,800 by dividing. And that gives me my velocity is, let's say, big velocity, 14,190 meters per second. Now that is not my answer. That's just what I could get right now. I'm still trying to find the mass, so I'm going to plug into my square root of gm over r equation. Now that I have velocity and I still have the radius, so now I can find m. It's going to be easier for us to rearrange first and then plug in, so I'm going to get m by itself. That way I'm not trying to do all the same steps but with really big numbers. So first I want to get rid of this square root. You get rid of square root by squaring. So v squared is v squared. Squaring the square root will leave me with gm over r. Now I'm trying to get m by itself. Get rid of the r by multiplying r up. I have r v squared equals gm. To get m by itself, you divide the g over. So m is r. V squared, the 14,190 squared, over g, which is 6.7 e negative 11. I got that my mass was 5.4 e26, and it makes sense it's a big exponent because it's talking about the mass of a plane. We're looking for the orbital radius when we're given gravitational field strengths. This is my little g. It is orbiting the Earth, so I'm going to use the mass of the Earth. Plug into our gravitational field strength equation. 8.68 equals big G, 6 point blah blah blah. Mass of the Earth is given over here, 5.98 e24 over r squared, and that's what I'm trying to find right here. Because it asks what is the orbital radius. It's not going to be the radius of the Earth because this is some height above the Earth. Unknown is on the bottom, so the first thing we're going to do is multiply that up. So r squared times this. And then I multiplied these and I got 4.0066 E14. Trying to get r squared by itself, so I'm going to divide the 8.68 over. And that gives me r squared as 4.615 E13. To get r by itself, we're going to have to take the square root, and that gives me r 6794040. And that's my radius, and it makes sense it's a big number because it is the distance from the center of the Earth to whatever height we're at. If the space station had 10 times the mass of the shuttle that we're talking about right here, how would that affect the speed? So think about your speed is square root of gm over r. The mass that we're talking about is that center mass, the mass of Earth. The mass of the space station actually doesn't matter, so it would have no effect. It wouldn't change the speed at all. If the space station moves to a lower orbit, this is going to be a smaller r. So if I have a smaller r, what's happening to the velocity? V and r are doing opposite things. So if I have a smaller r, this is going to be a bigger velocity. So I'm going to say a bigger velocity is just faster. And if it's going faster, it should take less time. It's going faster. So to lesser, I guess we could say shorter period. Two moons orbit the same planet, the same radius. So this is my planet, same radius. I have moon A, which is triple the mass of moon B. So moon, obviously not to scale, but a bigger moon and a smaller moon going around the same planet. It says the force between, I'll label it A and B, and planet. The force between A and the planet is greater than the force between B and the planet. Yeah, that should make sense because GMM over R squared to get our force of gravity. The planet would be the same mass, but then for A, it's 3M versus M, so this one should be a greater force, yes. The acceleration of A towards the planet is greater, so acceleration would be GM over R squared. The mass is the mass of the planet. So the mass of the planet should not have any, the bigger mass of the moon will not affect the mass of the planet, so they'll still feel the same acceleration. Because it's that second mass, it doesn't matter. The orbital velocity of moon A is faster, so V is square root of GM over R. Again, this is the mass of the planet, so the mass of the moon being greater will not affect the velocity, so not C. And then D, the period is shorter, while the velocity is the same, so their periods will be the same. So it was just A. Number 31, they go to two identical objects, go to two different planets. Planet A has a greater mass but the same radius, so something like this, but this one is like more mass. Planet A and B. If the object, is it true that the object on planet A has a greater weight? So FG is GMM over R squared. The planet mass is greater for A than for B, so yes, the force of gravity should be greater, that's true. It'll have a greater acceleration, so GM over R squared. I'm talking about the planet mass in this case, and the planet mass is greater for A, so that means the acceleration should be greater, that's true. And then it has a greater mass, that is not true. The mass of the object should stay the same no matter where it is. It's only the weight or the force of gravity or the acceleration that's changing due to location, because the gravity is changing, the mass is not though. Two identical spacecraft orbit the same planet but a different radii. So A is farther, so if this is like B right here, and then A is farther out, greater radius. It's saying A feels a greater acceleration, so GM over R squared. If I have a greater radius, that's actually going to be a smaller acceleration, so that is not true. A longer period, so period is 2 pi r over v. If A has a greater radius, which it does, then it would have a greater period, that's true. Faster speed, so this is velocity square root of GM over R. R is on the bottom, V is on top, so they do opposite things. A has a bigger radius, that would actually be a slower or smaller speed, so not C. And then smaller gravitational force than the other pair. This is my FG equation, so a bigger radius. These are opposite, a bigger radius would mean a smaller force, so that's true as well.